This lecture and the next two lectures we'll talk about axial deformation. We're going to first start off in this lecture talking about general axial deformation, bars that can have non-uniform cross sections. Maybe their material properties can change along their length as well. And in the next section we'll look at series or assemblages of statically determinate loaded axial bars, and then after that then we'll get into statically indeterminate axially loaded bars, and so we'll learn about what all those different terms mean as we come across them. So to start off with, we'll get into axial deformation, and to emphasize the fact that we can have a bar that has a non-constant cross section, we still want it to vary kind of smoothly. I'm going to show a tapering cross section. Let's see if I can draw this. So what I'm trying to draw is a bar that has a round cross section, but it goes from a larger diameter to a smaller diameter from one end to the other. Let me clean this up just a little bit. Now we still want this to be under axial loading conditions, and there are some requirements for that. If you notice, there's a line that joins the centroids of each of the cross sections of this bar from one end to the other. When we put an axial force on it, the resultant of the axial force has to lie on that line, has to act through the centroid of all those cross sections. I'm going to put a coordinate system on this bar as well. We're going to take the x-axis down the length of the bar. Should probably draw that down a little bit further, but that'd get in the way. So the x-axis is going to be down the length. The y and the z-axes will lie in the plane of the cross-section. So let's write down a few notes. So just what we mentioned, resultant force acting down the middle of the cross sections. What that does for us is that keeps us in pure axial loading and no bending. We'll talk about bending later in the course. A little bit more complicated stress distribution in that case. Now the bar could have a changing cross section as I've drawn here. I'll abbreviate that as X section. And in addition to that, the load could change along the length. And the material properties. All of these things can change with position X. All right. Now, because the bar has this taper to it, and the material properties can change and so forth, what we can end up with is what's called a non-uniform strain distribution in the bar. If you think about it, on the left, where the cross-section is not as big as it is on the right, material on the left can stretch out more easily than the material on the right. So we have a strain that can change with position X. This is called a non-uniform strain distribution. All right, now we want to take a look at the strain at a single point. On the next page, I'm going to make things a little bit easier on myself. I'm going to draw these as if these bars have a constant cross-section, but even though I'm drawing it with a constant cross-section, what I'm going to write down will apply to bars that have a non-uniform cross-section like this picture I have on this page. So to look at the strain at a point, I'm going to take a section of a bar, and I'm going to label 2 points on it, points C and D. Over on the left, this is the bar before any loads applied. So that would be the undeformed situation or configuration. And I got a couple points there, C and D. Point C lies at position X from wherever my coordinate system starts. Point D is a little bit further to the right down the length of the bar from point C. The space in between point C and D is the distance delta X. Soon we're going to shrink that delta X down to 0 to get the strain at a point, but we're going to start out with a little bit of separation for right now. Of course, in the bar, we could have a little bit different strain distribution from one side to the other. What I'm going to do is I'm going to take this bar and I'm going to stretch it out, and I can pick it up and I can move it over at the same time. So I'm just going to draw a little arrow here, and I'm going to write down, I'm going to stretch and move the bar. Now point C and D have new positions. I'm going to call those C star and D star. And if we stretch this bar out, the distance in between those points is increased. And now that distance I'm going to call delta X star. That's the final length in between those 2 points after it's moved. If we want to know what the strain is between point C and D, we can use our engineering strain formula, the change in length divided by the initial length. So let me just write that down. So delta X star minus delta X, that's the change in length, divided by the initial length, delta X. Now on the top, this term, delta X star minus delta X, what that represents is the relative change in length between, change in position between points C and D. I'll go over that again in just a second. So that's the relative change in position. So let's see, let's do an example. Let's say point C started out at position X equal to 1. Point D started out at position X equal to 2. After this thing is stretched out and or moved, maybe point C is now at X equal to 11. And point D star, I guess I should say, is at X equal to, let's say, just another number, 15. So obviously our original delta X was equal to 1, and this delta X star is equal to 4. And so the relative change in position is equal to 3. All right, so those points started out 1 unit apart, and now they're 4 units apart. So the relative change in position is 3 units. Another way to say the change in position is the displacement of a point. So we will be able to write the strains in terms of displacements. And the symbol we're going to use for displacement is a little u. Now the way that we can indicate displacement would be if I wanted the displacement of point C, and I would label that as u sub c, or I would say that that would be the displacement of the point that was originally at position x. If I want the displacement of point D, then that would be the displacement of the point that was originally at position x plus delta x. So you see up here, that was the original location of point D, was at position x plus delta x. Now if we want the relative change in position between point C and D, the relative displacement, then the way we can say that is this delta x star minus delta x can be expressed as the displacement of the point at position x plus delta x minus the displacement of the point at position x. All right, well, let's see if that works out. The displacement of the point C, which was originally at x equal to 1, it displaced 10 units to get us to C star. Point D, which was at position x plus delta x, it was at x equal to 2, it displaced 13 units in order to get us to x equal to 15. Okay, so 13 minus 10 gives us 3. So this, in terms of displacement, is just a fancier way of writing this delta x star minus delta x term. But it's the same thing. All right, so if the top can be written in terms of displacement u of x plus delta x minus u of x, then that means that the strain, then, the axial, extensional, or normal strain, be written in terms of this displacement as u of x plus delta x minus u of x divided by the distance in between point C and D, delta x. If we want the strain at a point, all we're doing is we're shrinking the distance between C and D down to 0. We're taking the limit as the denominator goes to 0, delta x, of u of x plus delta x minus u of x over delta x. Now, if you've been through calculus, that may look familiar to you. Hopefully it does. That's the basic definition of a derivative. And so this would be the derivative of the displacement function with respect to x. So what that means is if you knew what the displacement function is, and you take the derivative of it, then you have the strain anywhere that you want. You can imagine some sort of polynomial displacement functions. Maybe, for example, if the displacement is equal to some sort of constant C1 times x, then the derivative of u with respect to x would be a constant. So a constant strain comes about when you have what's called a linear displacement field. If you have a constant displacement, say C2, then the derivative of that with respect to x would be equal to 0, and you would have 0 strain. A constant displacement is what you do if you take a bar, or maybe your pencil, pick it up and move it over to your right, and you don't stretch it out whatsoever, every point on the bar has moved or displaced the same amount, so you have zero strain, and that makes a lot of sense. Usually, though, in mechanics materials, what we want to get is the displacement field, and we're not given the displacement field to begin with. So what we do is we just separate these terms and say du is equal to the strain, which can be a function of position, times dx, integrate both sides. All right. And if you have a length of the bar, you can integrate along its length, and then you would also have a constant of integration. Now this term for the displacement u, you see the term on the left that has the integral in it and the term on the right with the constant of integration. The term with the constant of integration is this rigid displacement term. It's what we talked about when we have taken our pencil or our bar and picked it up and moved it. So this is called a rigid body displacement. And this term on the left then represents the displacement of the bar due to stretching of the material. A lot of times in this class, we're going to be interested in the stretching of the material, and we're usually not as concerned with the rigid body displacement. In engineering applications, both of these will be important to you. Let's take a look at this integral in just a little bit more detail. So we have the integral of the strain with x along the length of the bar. Previously, we call the deformation of the bar delta L. A lot of books switch over to using the symbol little e to represent axial deformation at this point. It's the same thing. Our book, the book that I use, switches to little e, so I will use the little e to be consistent with it. But if you see delta L, it's the exact same thing. Well, there's different ways to write this integral. We know that if we have a uniaxial stress state, that we can use 1D Hooke's law. So what I mean by uniaxial stress state is that if we have stress, sigma, in only one direction, then we can relate stresses and strains by the formula sigma is equal to E epsilon. It's the slope of the stress-strain curve in the linear portion of the material. If that's the case, then the strain can be written as sigma divided by the modulus of elasticity. And this integral can be rewritten as sigma over E. So in some cases, like in the bar at the beginning that I had that had a changing cross-section, it may be easier to compute the stress in that bar than it is to know the strain in it right off the bat. So sigma over E integrated along the length of the bar will give you the stretch. We also know that if we have a uniaxial stress state, that the axial stress, sigma, is equal to the force divided by the cross-sectional area. I'll put the subscripts here, but I'll drop them later. So if we want, we can also write this integral just a little bit more differently. It's the same thing, but we're going to have F over A, and then divide that by the modulus of elasticity E, integrated along the length of the bar. We will work with this equation quite a lot, so let's write it down. Little e is the integral along the length of the bar of F over AE dx, where this little e represents the axial deformation, the amount of stretching of the bar, the change in length due to its loading. Here, F is the internal force. It could be a function of position x. A is the cross-sectional area. It could also be a function of position x. And E is our modulus of elasticity. that could also change with position x. Now, anything that changes with position x has to stay inside that integral. But anything that doesn't change is independent of x, the axial direction of the bar, can be taken out in front of the integral. And we'll work some examples of different sorts. First of all, let's consider the case where everything is a constant. Maybe that's the easiest. Let's start on a clean page and we'll take a look at it. All right, so we have our general form that has all these terms inside the integral. But now we're going to consider if these forces, areas, material properties are constant along the length. Each one of them can be taken out in front of the integral. And we're left with just integrating dx. If we integrate dx along the length of the bar from 0 to L, all we get is L. This is going to be a very important formula for us in this course. Little e is equal to FL over AE. So if I have a bar, let's do an example. Say it's 48 inches long. And we put 5,000 pounds on it. It has a constant cross section. Its diameter is 1 inch. And it's steel, so its modulus of elasticity would be 30 million, or 30 times 10 to the 6 psi. Then the axial deformation of the bar would be equal to FL over AE. We plug this in 5,000, the length of the bar, 48 inches. Need to make sure our units are consistent. The area, if it's a 1 inch diameter bar, we'd have pi over 4 diameter squared, and the modulus of elasticity of 30 times 10 to the 6 psi. And then we would end up with units of inches. Let's go ahead and calculate that number just to see what we've got. Let me grab my calculator. Comes out to be a fairly small number, 10.19 times 10 to the minus 3 inches. So just over 10 thousandths of an inch. 5,000 pounds is a pretty substantial force. If you're talking about a material like steel, steel is a very stiff material. Okay, so it doesn't stretch out very much at all, even though it has a 1 inch diameter. That's a pretty stout piece of steel. All right, so that's pretty basic. Now, you can also run into situations where you have segments of constant force, area, and material properties over the length. So let's talk about that. Okay, in this case, we have a bar. Let's just use 2 segments. Each of those segments has a constant force in it, by the way that I have it loaded. It has a constant cross-sectional area and constant material properties. Let's just say that. They could be different in segment 1 and segment 2, but so it's kind of piecewise constant. I've labeled a few points on there, A, B, and C, and the x position of those points. Point A, let's take that at the wall where our coordinate system starts, x equal to 0. Point B, let's just call that capital X sub B, and position C is capital X sub C. If we want to find out how much this structure elongates, how much its deformation is, we know that we have our general integral along the total length of the bar of F over AE dx. But since there are segments where these things are constant, what I can do is I can break this up into one integral from 0 to x sub b of f1 over a1 e1 dx, and a second integral that goes from position b to c of f2 over A2 E2 dx. Okay. But if I notice the distance from 0 to x sub b, that's the length of section 1. So in other words, I can write this as an integral from 0 to L1 of F1 over A1 E1. And then the B to C distance, that's the length of bar number 2. So I can just as easily write this as an integral from 0 to L2 of F2 over A2 E2 dx. Now if I look at these two integrals, that's just exactly the same thing as if we would have written it this way. If A and E are constant and F is constant over the length L, FL over AE for section 1, and then the second integral becomes FL over AE for section 2. In other words, the total deformation is the sum of the individual deformations, where little e1 and little e2 is the deformation of segment 1 and deformation of segment 2. FL over AE for each piece. Okay, so dealing with bars with multiple segments is pretty straightforward. Let's do another example, though, maybe one that's a little bit more tricky, a bar that has a completely fully changing cross-section. So let's look at this example, a little bit more general example, where we have a tapered bar. It means the diameter is bigger on one side than it is on the other, but in our case we want to have a linear taper. It's going to help us out a little bit. The length of this bar is L, and it has a force of F applied to it. It's made out of a single material with a modulus of elasticity E. We're going to use symbols in this example, and then later on we can put in numbers if we want to. If we want to find the deformation of this bar, little e, then we know that we can start off with our integral f over AE dx, integrated along the length from 0 to L. The things that are constant can be moved out in front of the integral. If we were to take a free body cut in any arbitrary position, no matter where we're at in this particular bar, the way this problem is set up, the force is constant. So the internal force is F. So that's a constant. We just said the material properties do not change with position x, so that can be brought out in front of the integral. But now in this example, the area of the bar does change. Okay. At any particular position x, we're going to have a different cross-sectional area. On the far right, the diameter is d sub L. On the far left, the diameter is d sub 0. The diameter tapers linearly. That doesn't mean the area tapers linearly, so you have to be kind of careful. We need to find the area as a function of x, the area of the cross-section of the bar. We can do that because we know for any particular cross-section, we can compute the area from the equation pi over 4 times the diameter squared, where this changes with x. So now what we need to do is we need to see how we can come up with an equation for the diameter d. The key to this, in this particular problem, is to understand that this is a linear taper, which means that the diameter follows the form of the equation of a line. Now you may remember, I'm sure you do, the equation of a line. Y is equal to mx plus b, where if you're given some x, the slope and the intercept, you can compute the y. Well, what we want is the diameter, and it will follow the similar type of equation. The diameter d will be equal to some slope times x plus some intercept value. In order to find the slope and the intercept, we need to know the diameter at two given positions on this bar. And in this case, we do. We know that at x equal to 0, the diameter is equal to d sub 0, d naught. And on the other side, at x equal to L, the diameter is equal to d sub L. Let's plug these things in and see what we get. In our first case, when x is equal to 0, we have d naught is equal to our intercept. And then in the second case, we have d sub L is equal to some unknown right now slope times the x distance, which would be L, plus the intercept, which is d naught. So that means that the slope would be equal to d sub L minus d naught over the length of the bar. So now that we know what the slope and the intercept are, we can go back here and put them in there for the area. So in this particular case, the area as a function of position x would be equal to pi over 4. And I'm going to leave these as symbols, mx plus b squared, where the m and the b are given by these equations here. If we had numbers, we could plug them right in. All right, now what we can do is we can go back to the integral, coming back here. Along the length of the bar, we'd have 1 on top because I factored the f out. And then I'd have pi over 4, the diameter squared, mx plus b, quantity squared dx. All right, let me clean this up a little bit and write this integral on the next page, and I'll show you how to do the math for that. All right, now the pi over 4, that's also a constant. We can bring that out in front if we want as well. Let's go ahead and do that. I'll write this one more time. We have the force in the bar divided by the modulus of elasticity, and the pi over 4 can come out on the bottom. And then we have an integral along the length of the bar of 1 over this quantity, mx plus b squared. Now I'm just going to leave that mx plus b like that. Even though we know what they are, we'll substitute them in at the end. If it's been a little while since you've done the integral calculus, you can use an integral table, but you may remember something from calculus called a U substitution. And this is a good place that we can use that. So we're going to let this capital U equal to mx plus b. The du would be equal to m times dx. So our dx is going to be equal to 1 over m times the du. So I'm going to rewrite the integral that we have here. I'm just going to do the integral part. This integral becomes an integral of, instead of dx, we're going to have 1 over m du, and we have u squared on the bottom. Let me write it this way, is 1 over m times u to the minus 2 power times du. If we integrate that, we can do that straightforward. We can add 1 to the exponent, and we're going to divide by the new exponent. So we have the 1 over m u to the minus 1 power. We're going to divide by minus 1. All right. Now, since we've done the integration, we can resubstitute in for capital U. Let's make sure we have everything written down. We have f over e and pi over 4. We have 1 over m and a negative sign because of the integration. We have u to the minus 1 power. Another way we can do that is we can write as 1 over mx plus b, that quantity. And then our limits of integration are along the length of the bar from 0 to L. I'm going to let you do this part, but all you have to do now is evaluate this, and you can find out an equation for the deformation of a bar subjected to an axial load when the bar has a linear taper. It's a fairly specialized equation, but you can imagine if you know how the diameter of the bar changes as a function of x, you can do all sorts of different integrals like this. All right, let's talk about this a little bit more, and then we'll do another example with some numbers. So we're kind of review some of these concepts. We went through and we talked about the strain at a point, and we were able to get the deformation of a generally shaped bar as an integral along the length of the bar of f over a e dx. In some cases, like we just worked, the area has to change. Area changes with position x. We have to leave that inside the integral. In other cases, the force or the material properties can change, and they would have to stay inside the integral. If things are constant, then we can bring them out in front. If everything is constant, then we have a very nice compact formula, FL over AE. And if we have a bar that's made out of a couple of segments, we can integrate that in a piecewise fashion, and the total deformation would be the sum of the individual deformations. If they are both constant force, area, material properties, and so forth, then this can be written as F1 L1 over A1 E1 plus F2 L2 over A2 E2. All right, so the next thing we'll do then, we'll save the numerical example for the next lecture, but we'll look at some assemblages of statically determinant axially loaded bars, and we'll talk about some details again, and we'll work some examples with some numbers.